Okay, this is going to be the lesson video for Calc 3, section 14.6, the directional derivative and the gradient vector and related concepts. So let me share the main notes with you, and we'll take a look. At one point, we'll switch out to some older notes and compare to something. But for directional derivatives, first a note. So I'm presenting these lessons in the order that it makes sense if you want to learn things in order to use them. But this is a different order than you would use if you're trying to derive the things from scratch. So the textbook presents this information in a different order because they're trying to develop the formulas, right? And I've got a separate document which is going to be included on the website, on my website, and also on Schoology if you're interested in the derivations. I'm not going to do any of the derivations. We're just going to state things to be true. And if you want to know why they're true, then I'll refer you to that other thing. Because if you go through it in that order, it's hard to understand how to use things. So this order is the one that Ms. Destu used in the class last year, which I agree is the better order if we're just trying to learn something for the sake of using it. But everything that we're talking about here is derived in another document. So you can read through that and then also just look at this lesson as a way as far as how to use these things. Okay, so first of all, we're going to define something called the gradient vector, okay? And so we'll start with a two-dimensional multivariable function. So we have z, scalar function, as a function of two scalar inputs, x and y. If z is a function of f, function f of xy, then we define the gradient vector to be the vector whose x component is the partial derivative of z with respect to x, and whose y component is the partial derivative of z with respect to y. So fx and fy, evaluated at some particular xy point. And the symbol for that is this upside down triangle, and then f at any xy. So this upside down triangle is called del, D-E-L. And it's a standard symbol used both in math and in physics. And it has this meaning that it's a vector whose components are derivatives in that component direction of the function, okay? It's always understood to mean a vector, so we actually never draw a line over it, even though you could draw a line over this because it's a vector. The line is omitted because it's never used in a non-vector way. Okay, so that's the gradient vector. Let's talk about what it means. So let's say you had some function. Z is a function of x and y, like 1/4 x squared plus y. There's a couple of typos down here too. This should be crossed out and replaced with 1, 1, and the gradient of f should be 1, 1, 0. If you want to make that change in your notes, if you have printed notes. Okay, so let's say I have a function z, which is a function of x and y, 1/4 x squared plus y. Then we can compute the gradient function, or the gradient vector. The gradient vector, del f, is we take the partial derivative of z with respect to x, which would be 1/2 x, and then we take the partial derivative of z, but with respect to the other variable y, and get 1, and then we just make a vector where this is the x component and this is the y component. So 1/2 x, comma 1. That's the gradient vector, okay? And we can evaluate all this at a particular point. So if I go to some point in the domain, like say 2, 3, okay, and I plug in 2, 3 into the original function, I would get 4, which is the height, right, if I'm representing this with a surface. And if I were to plug in, all the different domain x, y's in to get a surface, I get this kind of spoon-shaped curved surface like that, okay? Right, so right above it, though, there's a particular point on the surface right here. Right? And what the gradient vector shows is if you evaluate it at a point. So let's actually plug 2 and 3 into the gradient function. So if I plug 2 in here, I get 1. And if I plug 3 in here, there's no place to plug it in. So it's 1, 1. So that gradient vector 1, 1, what is that? Okay, so if you go on the surface and then you draw a line in the direction which would cause z to increase the most rapidly, the steepest increase, and then say, okay, in the xy plane, what direction is that pointing? In other words, just move it straight down so it's pointing only in the xy plane. That's the gradient vector. The gradient vector is in the xy plane in the direction where the surface is increasing most steeply at that point. Okay, so that's the geometric meaning of the gradient vector. It's the direction of steepest increase of the z function. Okay, but it's really a vector in the domain. Okay, that's the meaning of the gradient vector. It gives us the direction of greatest increase of the output function. All right, and we can use it to define something called directional derivatives. So let me share something more generally here so I can swap back and forth for a second. I'm going to share the whole screen. When we first talked about partial derivatives, right, we talked about partial derivatives like this, right? We said that the partial derivative of z with respect to y means you hold x constant, and you're saying how fast is z increasing or decreasing for every change in the y. So if I change in the y direction, maybe z is going down, so I would have some negative derivative. So this is a partial derivative in the y direction. And then if I want dz dx, that's holding y constant and moving in the x direction. How fast does z change for changes in the x direction, right? And then we said later we'll be able to do arbitrary directions. So now that we have the gradient defined, it turns out we can do that, right? And these fx and fy's are going to just turn out to be special cases of directional derivatives. Okay, so let me switch back to the notes, and we'll continue our discussion. And remember, all of this stuff is derived in that separate PDF if you want to see all the derivations of these things that I'm just stating are true. All right, so we know the derivatives are given in the x and y directions are given by the partial derivatives. What about derivatives in any arbitrary direction? Those are called directional derivatives. So first we need a way to define a direction, right? And direction is really defined in the domain, right? Because it's irrespective of the output variable, right? It's just a direction. So we define direction in the domain by defining what's called a unit direction vector, which is called u, okay? And so you can start at any point in the domain. The direction will be defined relative to the positive x-axis direction counterclockwise, the same as all trig angles are defined. We'll call that direction angle theta. And that means that the unit direction vector, since it has a length of 1, will have an x component of cosine of theta and a y component of sine of theta, as we always do when we go from magnitude and length to x and y component, okay? And so here's the idea. The idea is if we know the direction on a surface of maximum increase, okay, and that's the gradient vector del f, okay, then I can project a percentage of that in some particular direction by figuring out how much of that is projected in the direction we're defining. So if I have in the xy plane here an angle theta that defines a particular direction counterclockwise from x, then I can say, let's make a unit vector in that direction called the unit direction vector. That's u. That's a unit vector in that direction. And then some fraction of this fastest rate of change of z is going to be in that direction. And all that's going to be is the projection of the gradient vector onto that direction. And we know that to do a projection, we just take the dot product, except that what we're projecting onto has to be unit vector. Right, so it turns out that what we define as the directional derivative, which is written this way, a capital D for derivative u for a direction. In other words, the derivative of how fast is z changing in the u direction of some function f at xy is the gradient vector at a xy value, and then the dot product with the unit vector in the direction we want to know the rate of change in. Okay, so this is the very important definition of directional derivative. It's the dot product of the gradient with a unit direction. Okay, so in fact, if you wanted to kind of talk about this a little bit further, we know that dot products are equal to the magnitude of one vector times the magnitude of the other vector times the cosine of the angle. And so since cosine is going to be maximum when the angle is 0, then that means that the directional derivative will be maximum when you're pointing in the direction of the gradient, right? If you're pointing in the direction of the gradient, you're going to get the max change, right? You're going to get the minimum change when these are perpendicular, and you'll get 0 projection. So when you're moving in a direction that's perpendicular to the gradient, you will always have a change of 0 in the z direction. Okay? All right. Okay, super important, the direction vector has to be a unit vector, otherwise the calculation is messed up. And it's because we know that when we said we have a dot b, right, I have to project one thing onto the other, right, whichever one that's setting the direction, that one has to be turned into a unit vector. Otherwise, we don't have a meaningful projection number. So you have to have a unit vector in the direction, and then take the gradient dot that unit vector. But this has to be a unit vector. Okay. So all these ideas are luckily extendable with no changes into any number of higher dimensions. So if you have, say, w as a function of x, y, and z, where the domain is 3D space now, you can't really graph it very easily. The gradient vector would be partial of the function with respect to x for x, partial with respect to y for y, partial with respect to z for z. And the direction can be the gradient dot a unit vector, but this unit vector can be anywhere in 3D space, not restricted to the xy plane because the domain is 3D. So all these ideas are extendable into any number of dimensions. Let's take an example and look at it in detail. So this is actually from the book. So I'm using this one so I can use some pictures from the book. Let's say we have z is a function of xy, and it's x times e to the y. And we want to find the rate of change of output for f at the particular point x is 2, y is 0, in the direction from that point to the point 1/2, 2. Okay, and then we're going to answer in what direction does it have the maximum rate of change, and what is that maximum rate of change. Okay, so to start with, right, everything is going to begin from finding the gradient. So the gradient of that f is fx fy. Another way to write it would be partial derivative of z with respect to x, partial derivative of z with respect to y. Same thing. We're going to find the partial derivatives. So the partial derivative of x, if x is considered the variable, everything else is a constant, the derivative would be 1 times e to the y, right? And then treating y as the variable and x as a constant, it's the constant x and the copy derivative of e to the y. So the gradient vector would be e to the y for its x component and x e to the y for its y component. Okay, and then we can evaluate this. So that's at any xy. We can evaluate this at a particular xy, like 2, 0, by plugging in 2 for x and 0 for y everywhere in this expression. So that would be e to the 0, 2 times e to the 0, which would be 1, 2. Okay, so this vector gives me the direction in the xy plane that the z is increasing the most rapidly on the surface. Okay, so actually let's right now say in what direction does this have this maximum rate of change? It's this direction, right? If I wanted to find in terms of the angle, I could do the inverse tangent of 2 over 1, but this establishes the direction. This gives the establishes the direction of maximum rate of change. Right? If I go in any other direction, z will change less rapidly than if I move in the direction of 1 unit in x for every 2 units of y. Okay. All right. And then we want to find the rate of change, right? So now the rate of change, that's the directional derivative. So the directional derivative in the direction u of f at, well, first we'll do xy. That's going to be the gradient of f at that xy, and then the dot product with u. So first we need u. Okay, so u is going to be the vector from this point to this point. So that's going to be 1/2 minus 2 in the x direction, 2 minus 0 in the y direction. So that would be -3/2, 2. That's the direction we want to go. I need to make that a unit vector, so I have to divide that by the square root. So actually, let's do it over here. Divide it by the square root of, let's see, 3/2 squared plus 2 squared, right? Which turns out to be, what does that turn out to be? It's going to be the square root of, let's see, 9 fourths plus 4. So 16 fourths plus 4, which is 25 fourths, 25 over 4. So I think that's going to be 5/2. Yep, 5/2. So this would be -3/2 over 2 divided by 5/2. It's very important that this is a unit vector. And then that means that if you divided this, this would be -3/2. And then, let's see, 2, 5, right? -3, is that right? No, -3/5. Yeah, -3/5. and then 2, and then 5. Is that right? I think my published notes here, that can't be 5 because that wouldn't be a unit vector. So negative 3 halves divided by 5 is negative 3/5. This would be 2 divided by 5 halves, sorry, which equals 2 times 2/5, which is going to be 4/5. There we go, 4/5. Okay, so this is the unit vector. And now that I have a unit vector in the direction of maximum rate of change, or the direction that not the maximum rate of change, but that I want to move along, I can find the dot product to project some of this gradient vector. So I've got the gradient vector 1, 2, right? And if I take a dot product with this negative 3/5, 4/5, that's going to tell me how much of it is in the direction that I wish to go. So it's going to be 1 times negative 3/5 plus 2 times 4/5, right? Negative 3 and 8 is going to be, let's negative 3/5. Let's see, negative 3/5 plus 8/5, 5/5. So it's going to be 1. Happens to be 1. Okay. And then what would the maximum rate of change be? Let me go back to green and show that. So the max rate of change, max derivative, would be just the gradient itself. If I took the magnitude of the gradient itself, that's going to be the square root of 5. So just the square root of 5, a little over. So 2.23. So basically the fastest that you'll go, if you're at the point on the surface above 2, 0, the fastest that you'll go is about 2.25 up in z for every 1 unit that you change, right? But to go from this to this, it's a different direction, which is not the max rate of change. And in that direction, it only increases 1 unit in z for every 1 unit in this direction. So this is the directional derivative, which is a percentage of the gradient, which is the maximum rate of change. All right, just to kind of see some pictures of this, the book has some nice illustrations. First of all, right, here is a level curve drawing of this function on the xy plane, the level curve. So there's a surface above here, and this shows kind of the level curves and then flattened down onto the xy plane. So these are for different values of f. So the surface is 2 high at this location. It's 4.5 high here, 6 high here, 8, 10, and so on. It's growing up, like it's sort of like a topographical map, and this is the top of a mountain up here. All right, so PQ would be the direction between the points. We want to move from point P to point Q. That's this. The first thing we did was we found a unit direction vector at negative 3 has 4/5. That's a unit, that's that same direction, but only 1 unit. Okay, and then at this location, the gradient vector turned out to be 1, 2. So 1 in the x for every 2 in the y. This is the direction in the xy plane that we would go if you want to have the maximum increase in the function value. Okay, and the length of that is the square root of 5, 2 point something. Okay, so for every 1 unit that we travel in this direction, these functions go up, or these function values go up by the square root of 5 for every 1 unit traveled there. But then we picked this other direction, so when we projected this vector on the gradient vector onto the direction vector, we ended up getting a magnitude of 1. So if you go in this direction, right, although we're still increasing, we're not increasing as steeply. It takes us quite a while to go from 2 even to 4.5. So we only go 1 up in the z for every 1 unit traveled in this direction, as opposed to over 2 units in z for every unit traveled in this direction. Okay, since this is really 3D, I tried to take their picture and make a 3D picture, which would look like this. Right, here's those same level curves, x, y, z down here. There's really a surface showing f from 2 to 4.5 to 14 to 20 and so on. Right, so this blue gradient vector down here points in the direction of maximum increase. Right, but if we choose to go in some other direction, like say this direction, we're not going up as steeply, right? So this will not have as large of a change in z in that direction as we would if we went in the max direction. Okay, I'm just drawing a lot of pictures to try to help you see this. It's very hard to see, and especially hard, I think, if we were in physical class, I could try to use space to show this, but I think pictures really are key to understand this. All right, so if we understand that idea of gradient and how it's the direction of maximum rate of change, and how we can use it with a projection on a unit vector to find the direction in any arbitrary direction. You can kind of see how the fx and fy are just particular special cases of directional derivatives, where the angle is 0 or the angle is pi over 2, right? All right. So the next thing we're going to talk about is tangent lines and tangent planes. So if you look at in the xy plane what's going on, right? The gradient vector is moving towards the most rapid way you can increase in these function values, right? And so if at the point of contact of any of these level curves, you drew the line that was tangent to the curve at that point, these green lines, these are called tangent lines. And again, in that separate document, I derive and prove why those have to be perpendicular to the gradient. It turns out that they look perpendicular to the gradient because they are, right? If you go in any direction other than at right angles to the level curves, you will be increasing more slowly than you would. Basically, if you walk in any direction other than straight up the hill, then you're going to have a less steep slope, right? If you want to have the steepest slope, you'll always be walking directly up the hill, perpendicular to lines of constant altitude. Okay, so the tangent lines are shown in green. Okay, now if you add another input variable, so you have, say, w as a function of x, y, and z, where we have a three-dimensional gradient, right? And the unit vector is now three-dimensional, and directional derivatives are three-dimensional. The domain is 3D, right? Then that means that these maroon level curves would become blue level surfaces. They would become level surfaces like this, like shells of surfaces, right? And then instead of having tangent lines, like these green lines, we would have tangent planes at a particular point. And it turns out that the gradient is perpendicular to the tangent surfaces and perpendicular to the tangent, therefore the tangent planes, because that's the direction of maximum increase of the function value. But it's much harder to draw because the domain itself is 3D, and then each one of these surfaces would have a particular fourth dimensional number, right? So instead of level curves, we have level surfaces. Instead of tangent lines, we have tangent planes. Okay, you can actually figure out what the equation of a tangent plane is. This is also derived in that separate PDF. The equation of the tangent plane turns out to be related to the partial derivative. So if you take the partial derivative of f with respect to x and y and z, those turn out to be like the slopes of a plane. And then the variable x minus x0, y0, z0 is the point of contact where you're interested in finding the tangent plane at that location. Okay. All right. And the gradient would be perpendicular to that tangent plane at that point. Okay, that's it for concepts. One homework problem I thought required a hint. So number 29, I just put this up here. You can read it. It says, find all points for which directions of fastest change of a given function is 1, 1. That's actually equivalent to asking you, what xy points would the vector be parallel to 1, 1, meaning equal to a scalar multiple of 1, 1. So you end up solving, okay, the gradient of the gradient vector has to be a scalar multiple of the vector 1, 1. So if you use that as a hint, hopefully you'll be able to solve that problem. All right, that's it for section 14.6. And then we've got 2 more sections in the chapter here, but this will wrap up this video.